Thank you for being here, everybody. We're delighted that you could take the time to come and join us on a beautiful Friday afternoon here in Grove City. My name is Luke Rumbaugh. I teach in electrical engineering, and I've had the pleasure of working with a lot of these great students who are in the front of the room and also around the room. We're going to start off today with a presentation from the Astrobotic Sun Sensor team. It's a team of a mix of mechanical engineers, electrical and computer engineers, and applied science and engineering majors who have been doing some work with Astrobotics, which is a lunar delivery company right here in Pittsburgh, Pennsylvania. So, Mark?
Yeah. Hi, everyone. Thank you all for coming out today. We're really excited to show what we've gotten to work on over the last 2 semesters. My name is Mark Van Horn, and I've been the team leader for the last 2 semesters.
I'm Noah Lawler. I'm Luke Young.
Christopher Klein.
Jack Johnston.
Jared Schwartzer.
Anthony Fiorenza.
I'm Caden Draco.
Yeah, and we're very excited to show you what we've managed to make this year. So we wanted to start off with some necessary background, right? So sun sensors fundamentally determine where they are in space based on the angle of sunlight coming in, detecting that, and then sending that to their main computer. These sensors, while they can be extremely accurate, have a very limited field of view, so they usually come with multiple sensors surrounding the body of the ship, so that the sun will be in view of at least one of them throughout that process. Designing electronics for space has proved to be particularly challenging, as a lot of concerns that you wouldn't expect to have on Earth are very much present. That being vibration during launch, heat transfer doesn't occur through air, and radiation can severely mess up electronics over time, increased exposure. Going into Astrobotic technology uses these sun sensors on their lunar landers for a very similar purpose, to track their lunar lander location through space. To test these systems, they usually apply their hardware-in-the-loop simulator, and then they will hook that up directly to their flight equipment, which will allow them to see how their physical flight equipment will work as if it were in a real life environment and flying through space. This allows engineers to go into the actual launch with significant more confidence, seeing how it would interact with edge cases or normal scenarios. So our primary motivation for this project was Astrobotic needed their own sun sensor that they could design, implement, and move the design in the direction of their company's desires. This manifested in our problem goal, which is development of 2 systems. One system being the sun sensor itself to design, then track the sun, and then report that angle back, and a test bed to verify the integrity of this sensor. We have broken that goal down into 6 main objectives, 3 for the sensor side and 3 for the test bed side. These have been followed throughout the presentation throughout the last semesters. The idea being, if we've successfully completed all 6 of these objectives, then we will have a working product to deliver to Astrobotic.
Yeah, so a lot of that's very abstract. So what did we actually produce this semester? As Mark said, we have 2 major systems that we're delivering to Astrobotic. One of these is the sun sensor. This is a small sensor. It's about this size, and that sensor can detect what angle the sun's light is coming in. It's all well and good to design a sensor, but you need to confirm that it actually works and test it in real scenarios. Enter the test bed. The test bed is a gimbal system which rotates the sensor and provides a light source that can actually simulate the sun itself, and that way rotate the sensor around in real time as if it were flying through space. Next up, we have a live demonstration of what this would look like. So on the right here, or on your right here, you can see what the gimbal is actually doing. We're moving about in 2 axes, our pitch and our yaw axes. You can see there. And then on our left side, you can actually see a visualization of how the program is running. This blue angle you're seeing here is the command that we're sending to the motor, to the test bed, of where the actual position should be. And then this yellow vector you're seeing is what we're actually receiving from the sun sensor, and this is how we would verify or calibrate our data in our sun sensor so that we can reduce any inaccuracies or any errors. At this point, you can see on our left, we'll go into a little bit of a focus on our sun sensor, as that's our upcoming system. You can see on the left here, we have our 3D CAD model of the sun sensor board. On the center here, you can see we have our physical board here actually laid out and placed inside the sun sensor housing. And then on the right, you have the final sensor of what it will look like, of what it looks like completely housed and enclosed inside of its housing. Now, at this point, there are some key specifications that we want to talk about that we were asked to meet. So our sensor resolution, we needed to have less than a 0.5 degree resolution and a less than or 0.5 degree accuracy. Some power draw, we wanted less than 2 watts, and that's another big one that we want to hit on is our field of view. We needed to meet a 75 by 75 FOV, and we'll go into more on that later.
So this is an overview of all the subsystems that we use in our sensor. We first have an external housing, which has an aperture that allows sunlight to enter the sensor. The sunlight is then transmitted into electrical signals, then pass through several different stages. A filtering stage, an amplification stage, a processing stage, and then a transmission stage to the whole simulator system. We provide power to our sun sensor via unregulated voltage coming in from the test bed. Once it comes in, we have an onboard power system that will then regulate this to the necessary voltages that we have through all of our different systems. It will then distribute this power to the various systems. And then we also have to deal with heat. So heat is generated by all the electrical components that we have in this board, as well as sunlight hitting the external housing. The housing itself is able to pull this heat down to the base plate, which then interfaces with the lunar module to get rid of the heat out of the sun sensor and off to the lunar lander. We also have a temperature sensor to provide us accurate data of how hot and what the accurate temperature is of the current sensor at all times.
So the optics and the signal processing is responsible for taking in the sun's light and then converting that into electrical signals that the rest of the system can read and then calculate where the sun's direction is actually coming from. The main component that drives this is called a 4-quadrant photodiode. In the top right, you can see what one looks like. This is the one that's currently in our design. The way that these are laid out is they have 4 quadrants that are photodiodes. They're activated when light hits them, and depending on how much light hits them, they produce a linear current from that. That current is then passed off to other systems, and we can calculate where the sun's direction is. We have a quick visualization of how this works. You have an aperture above, which projects an image of the light onto the actual 4 quadrants, and then depending on how much light is on each of those, you get a centroid value that you can convert into the angle of the sun.
As you may imagine, the selecting of the 4-quadrant photodiode is a very big part of this process. The ideal sensor that we found was the Hamamatsu sensor, which is up in the top. This sensor is a surface mount, has a very large active area, and very, very tiny edges in between the active areas, which minimizes a big risk or a big error factor. Unfortunately, this part was not in stock and in back order in Japan for many, many weeks. So we have a stand-in part that works in with the rest of the system. Nothing else needs to be changed. And the only downside is our field of view, instead of being 75 degrees with the Hamamatsu sensor, is at 36 degrees. This can easily be changed in the future. The one thing that both of these sensors do is produce a very, very tiny signal, tiny current signal, which is too small for our systems to read naturally. So, naturally from that, we have to amplify and filter the signal. So, after light has hit the photodiodes, each of them produce their own amount of current, as Noah said, and these tiny currents need to be amplified, brought up so that it's to a level that is able to be read by the rest of our equipment, and that amplification incurs a lot of noise, which then needs to be filtered out with the capacitors. The force signals, after they've been amplified and filtered, are then sent to our MCU for further processing.
The main next piece of our design is all of the computation and communications. Computation and communications are responsible for taking that analog data that we read off those photodiodes, converting them into digital signals, and then doing all of our math and calculations on an onboard processor. A small computer on our board does all of that math and then sends it to our communication systems. What can we do with the data if Astrobotic can't use it on their lander? So we need systems to actually send that data over lines that they can communicate with and receive and send data back. The main component of the computation side is a microcontroller. We went with an 18 mega 64M1. That's just a type of microcontroller that's very small, has a low power draw, but has enough processing to handle the capabilities we needed. Another advantage is that this part is easily upgradable into a space-grade equivalent. The product that we're delivering to Astrobotic is a prototype. It's not one that would go onto a lander itself, but it's one that we'd like to be easily upgradable into a version that could put on a lunar lander. The other component of this that we designed is we have a nice programming port up here. That way, if any calibration or adjustments need to be made in the program, all you have to do is plug in and you can program on the fly and make it very easy to do that. The main program functions in a simple loop with most of everything else interrupt driven. The loop runs at 100 hertz. Inside that loop, we read the sensor data, we calculate our current sun vector, we filter out any data that's bad and check any other integrity of data, and then process any communication requests coming in. On the communication side, these all happen via interrupts. So if Astrobotics Lander says, hey, I need a piece of data from the sensor, it requests, it loads into a buffer, and then once we get to the process comms, it immediately receives that, processes it, and sends it back all within 10 milliseconds. These sensors, while they produce accurate results, they're not very good without calibration. Calibrating a sensor, part of the advantage of having a test bed is that we can go and put our sensor on the actual test bed, check a variety of angles, and then read what signals we're getting back to improve our accuracy. The way that we do this is we take scans across horizontal and vertical angle differences on our actual sensor, and we store those onto the microcontroller, and then we can look at those, interpolate between them, and find a much more accurate value that corrects a lot of the nonlinearities, or when you manufacture any tolerances, discontinuities. In the graph on the right, you can see that even just a translational error on the sensor of 0.15 millimeters can create a 10-degree error at the maximum. When you calibrate that, it'll reduce it to 0.1. So it's important to calibrate these sensors to get rid of any of that errors. The last thing to calibrate is temperature error. Photodiodes produce some level of dark current. That's current that flows even when there's no light. At low temperatures, this doesn't really matter. When you get up to about 100 degrees Celsius, which can happen in space, this can dominate the signal up to about 25% of your signal will be just dark current, and that throws off all your calculations. So we have an onboard temperature sensor directly below the photodiode that we can use to subtract out this value and fix all of our values.
Now, what is all of this data if you can't even send it anywhere? So our communication system relies on two main systems, our CAN bus and our RS-485, which is a full duplex system, which we'll go into here in just a moment. So I'm really proud to announce that both CAN bus and RS-485 are implemented and fully working. The CAN bus was a rather simple pick-and-place component. It has its hardware protocol, which is the encoding on the lines. It's whether or not we're driving a high or a low bit for different encodings. And it has the software implemented completely as well. So it's really, you just pick it and you send a message to it and it sends it on its way. Now the RS-485 is a little different, and it's a little atypical on the style we're using. We're using a 4-wire RS-485, also known as a full duplex. Now a normal RS-485 uses 2 wires, it's called a half duplex, and that sends the data receive and transmit on both just 2 lines. And it's called a differential signal, where one is driven high and one is driven low, and that difference determines what you're encoding. Now that actually is good, but that means you can't receive and transmit at the same time if you just have a half duplex. That's why we use the 4-wire full duplex that allows us to receive messages from the astrobotic in-flight computer on the lander craft, and that also allows us to respond to them at the same time as they're requesting things, so we can make sure we're not interfering with any communications. Now the problem with RS-485 as well is that it only defines the hardware protocol. It does not define the software. And so that means that we had to come up, as you can see here, with a sort of header or organization system of how our messages are defined and sent. You can see from the sync down to the code portion of this, that's what we call our header. That's just the information on what this message is actually entailing. And then you can see our data is our payload. It's what we're trying to communicate to them. And then at the very end, we have what's called a checksum, which just goes through all of the data and verifies that it's correct and that we haven't sent any miscommunications. Now, again, what is all of this if you can't even power it? It's just a brick. So here we have our power. We are designed for accepting 12 volts DC from the lunar craft. They are regulating that for us. And we're designed as well to draw less than 2 watts. At first, we receive possibly 5 to 36 volts. That was a requirement that ended up being changed. But we can take that from any lander craft into our buck converter, and that comes down to a 5 volts. It's from a switching frequency, so it does introduce some noise. And so to reduce that, we have what we call a filter circuit, which is just a capacitor and an inductor that helps smooth out that signal and keeps it nice and clean, so we can actually use that power without risking any components. That 5-volt thing goes out to our components like our microcontrollers and our amplification systems and even the photodiode itself. So it was absolutely important that we made sure that signal was as clean as possible. And that 5-volt is also used it comes down to a linear regulator, which just burns it off in a small amount of heat. and it burns it down to 3.3 volts, which we can then use to power our communication systems to communicate with the in-craft computer.
So looking now at the actual sun sensor housing, it is also very important to keep all the components cool because they're very harsh environments that they encounter, including direct radiation from the sun and vibration encountered on takeoff. So the sun sensor housing has to be able to hold these precisely and securely to the spacecraft while also keeping it cool when in a vacuum. So there's no air in space. So it can't be cooled by convection. It has to be cooled by conduction and radiation. So the housing material and the housing design were very important for this. So looking at some general design components, the actual housing is manufactured with black anodized 6061 aluminum, and then there are two parts, a housing top and a housing base. The housing top has the actual aperture that is used for the sun sensor, and then there's also a nesting, a fiducial that is used to integrate with Astrobotic's nesting pin system for assembly and calibration. Also, the PCB and the sun sensor is mounted directly to the top to keep a consistent distance between the aperture and the sun sensor surface. The base of the housing is used to hold the entire housing onto the actual spacecraft. There's 4 bolts to keep that very secure and rigid. Thinking back about the different environment conditions, there are a couple simultaneous heat loads that it experiences, and the housing must be able to keep the sun sensor and all the components in between -50 and 100 degrees C. So an ANSYS simulation was used on all of my designs to check and make sure that it could handle it. The analysis on the final design showed that the maximum temperature is only 27 degrees, which is well within the range that was required. And the maximum temperature, as you can see, is right. It's actually not on the aperture, it's right below. It's on the sun sensor surface, which it's encountering that because it has direct radiation from the sun, as well as heat generated by the board that the sun sensor is actually on. So that's what the maximum temperature is. In this model, the board was modeled with a fiberglass copper composite to model the board. In the next iteration of this analysis, a more accurate model of the board should be used. Likewise, a random vibration test was run on all the designs, and the NASA GEVS standards were used as the acceptance levels for this test. So the analysis on the final design showed that the maximum stress experience was only 1.17 megapascals, which is well below the yield strength of aluminum and the fiberglass board. Additionally, the maximum deformation of the sun sensor and the housing was very low, showing that the entire system is very rigid and sturdy and won't fly apart on takeoff. In the next iteration of this analysis, a solder joint analysis should be done to confirm the stability of the actual module.
So to integrate all the electrical systems we've talked about so far, we designed a single printed circuit board, or PCB, to fit inside the housing. This circuit board is 2.5 by 2.5 inches square and has 6 layers. All of our electrical components are on the top layer, with the exception of the photodiode and temperature sensor, which is on the back layer. The middle layers are used for signal transmission between components, power distribution, and also some grounding planes just to help mitigate any noise induced by some of the high-frequency devices. We also, because heat is an issue in space, and we want to make sure our board is conducting that evenly, we have plenty of thermal vias scattered throughout the board that will bring the heat evenly across the board. And on the bottom side, we use exposed copper pads so we can bond this directly to the housing and take the heat off the board and send it to the housing, which will then take it to the base plate and then to the lunar lander. We also use micro D connectors, and those are on the top of the board, and those just provide power and data communications to the sun sensor from the test bed.
Now, at this point, it's all well and good. All you've heard is engineering speak. What did we actually accomplish? So here's a stoplight of what we've got. Our worst case resolution sits at about 0.33 degrees. Our power draw, we crushed massively. We're under 1/8 of what we were asked of. We're at 0.23 watts. I will highlight some key areas to take note of. Our field of view right now, as we said before, we're only at 36 by 36. That's due to a part that got delayed. And then our accuracy, we're asked of 0.5, but right now we're at 3 degrees testing, and that is without calibration. Again, as you heard before, with a 10-degree error, we can get that down to a 0.1 degree. So this is not a concern at all.
Yeah, so moving into the second system of this project, we have the hardware in the loop test bed. Inside the second system, there are two major parts. There's the gimbal, as previously mentioned, to test the actual sensor itself, along with a blackout box. This blackout box contains a light, a gimbal housing, and all the electronics needed to function the blackout box and gimbal.
So like Jared said, there's a lot to go on with this test bed. As you can see here, this is a broad overview of what we've designed. Power enters the system and controls two microcontrollers, the sensor, a motor control, and a dimming board. The first microcontroller is paired up with the interface board, which will go to Astrobotics simulator. The second microcontroller controls the motion of the two steppers within our system. This is moving the gimbal, which is moving the sensor. First, we're going to be talking about the blackout box. So the purpose of the blackout box was to eliminate all ambient light from reaching the sensor. As one would mention, having ambient light could mess up your data, so you want to make sure it's as accurate as possible. We wanted to make sure that the test bed was blocking out all external light, and we wanted to keep it within a cubic foot, but this was a loose requirement as we went along with the project. So some features to the blackout box to note. The base plate was made out of steel and welded 4 bolts on the bottom. This was done to create a consistent mounting point so the test bed isn't rotating or having a different position while testing. The shelf is another part, is a 3D printed piece which is housing all of our electronics. This was made to keep it out of the way of the gimbal and keep our electronics neat and orderly.
Yeah, so moving on to the actual sensor testing system, we created a gimbal. So the purpose of the gimbal, as previously mentioned, was to actually test the sun sensor itself. So by doing this, we have 2 working portions. The reason that we have these are to create 2 different degrees of freedom when it comes to moving the actual motors in the system. So for the gimbal design, we have 2 motors that are previously set. One is to control the yaw direction and one for the pitch. We created a lower system and an upper portion. The lower portion contains a mounting base plate that will be connected onto the blackout box. Again, as Tony said, the reason for this is to create a constant mapping for where it would go. If you offset that at all, it could cause the center of rotation to be off a little bit, and it would cause the errors in the actual testing of the sensor. Along with that, all supports are made of 1/8" stainless steel. This is to make it rigid so it won't move at all during function, and any unnecessary torques will affect it as much as other materials. A gearbox is needed. Katie will get into that later as to why we needed that. And there's also lower limit switches to verify the yaw direction. So when the system is running, the yaw axis will turn, hit each limit switch, and then find the 0 position based off the limit switch. On the upper portion, we designed it to minimize as much weight as possible. So we made it out of aluminum, all parts except for the limit switch mounting platform, which is actually made out of PLA, 3D printed. The reason for this was to minimize that weight that the lower system would actually have to turn, so when it stops, it won't shift it, it won't cause any unnecessary moments of inertia around that point. Additionally, we have a mounting point for the temperature sensor on the center of the platform, so indicated by the arrow. The reason for this is we want to verify that there's actually a temperature reading on the outside of the housing to verify that that is what we anticipate it to be. Additionally, there are side limit switch mounts and limit switches on the non-driven side. Again, the reason for that, for when the system starts up, you must verify the true 0 position and make it in plane with the light source. So it'll go up and hit each limit switch, find the 0 position, and that will be centered in the system accordingly. On the non-driven side as well, there are batteries inside of there just to minimize drag or any friction that the system might feel during the actual production and use of it. Additionally, there's another gearbox on the driven side with a motor connected to it. That's, again, capable of that soon. So all put together, the system will look as follows. On the far left, that's a top-down view at the front of the gimbal. So you'll see on the left, I pointed out the limit switch mounts on the blue platform, if you will. And on the middle, you'll see the temperature sensor, as indicated, and the limit switches here and here for the yaw direction. Those were the pitch. And then this is the front view that the light would see during use. So this is the actual sensor mounted on. This is the yaw, and that would be the pitch direction. And that's what the light would actually see during the function of the test bed.
Okay, so now that we've talked about the different parts of our gimbal, we want to know how it actually moves. So the motor we chose was the NEMA 17 stepper motor. And this motor, along with a lot of other stepper motors, they have a step size of 1.8 degrees. Our requirement was 0.5 degrees of accuracy, and in order to accomplish this, we needed a gearbox in order to bring that accuracy, accuracy up and step size down. So on our on the y-axis, we have a 4-to-1 gearbox, and as you can see, it has a step size of 0.45 degrees. And on our base, we have a 20-to-1 right angle gearbox, so we're able to put the motor in and have it work properly. And this one has a 0.09 degree step size. So the main goal was to make sure that these were working properly. And unfortunately, we were not able to fully integrate our encoders as we were hoping to initially. But, the next slide, we have our code. And this code is able to take 3 main types of commands. So we have the move command, which is pretty straightforward. It takes angles and it moves to a spot. We have our light command, which will take brightness and either dim or brighten the light. And then a homing command, which will move the motors back to its home position.
We needed a way to connect our sun sensor to our test bed, so we create a PCB. It is a test bed interface hat. This hat will sit on top of an Arduino microcontroller, and all this hat does is it processes the data communications from the CAN and RS-485 signals from the sun sensor. It takes these and decodes them, and then sends that data to the microcontroller that's connected to it. The microcontroller will then send this to Astrobotics simulator. It also provides power to our sun sensor, and these are both the same microbeam interfaces as we saw on the sun sensor.
So now we're actually getting to the sun part. To test our sensor, we needed to have a light fixed to our blackout box that we could use to mimic our sun. So we needed something that got to about 1,300 watts per meter squared and reached AM0 light source. AM0 just means air mass 0, so the light that you would experience outside of our own atmosphere, non-scattered. So here you can see that we decided to go with a high intensity LED light. This was done because of our size requirement and because of our budget. This is the mount that we designed for to place the LED light onto the blackout box. We decided to go with a 2-piece mount with a base and a cap. The cap houses the LED and with tight geometries to make sure that it's not wiggling around and keeping a consistent flow of light towards the sensor. And the base, which is mounted straight to the side of the box, which the cap can screw onto.
All right, now regarding the test bed power system. The power system the test bed is entirely powered from a 120 volt on one side of it. That one switch is sent through a main switch and then a 6 amp low fuse in case there are any shorts. It won't keep drawing power from the line and start a fire. The 120 volt flows into a dimmer switch, which controls the LED and can control that brightness. And then it also flows into a 12 volt DC power supply, which powers both of our controllers and then the motors themselves through an e-stop. In case anything is not moving properly, you can just hit that e-stop and the system will stop without shutting everything else down.
Here's a picture of the shelf mentioned earlier of all the electronics. As you can see here, we split it up into 2 sides. We have 120 volts coming in on one, and we have the 12 volt that's powering most everything in the sensor. We wanted to divide it for safety because touching 120 volts on accident is not fun. So here's the deliverables for the test bed. We were glad to hit that the light source was able to be dimmed. We have all ambient light that's protecting the sensor. It's all powered by 120 volts. We had some close calls. Our motors didn't quite meet the 85 degrees that we would like. Right now it's actually getting to 78 degrees. And of course we talked about the encoders and the temp housing. We were not able to implement this at the time.
Yeah, so moving into the budget, we were allotted around a $4,000 budget for this project. We initially anticipated that it would cost around $1,800 to produce a working model. There were some unnecessary expenses. We spent a couple unnecessary expenses on some motors. It cost more than we thought. Additionally, we thought that it was going to be a little cheaper for the actual photodiodes. The photodiodes cost a lot more than we anticipated originally. And on parts alone, we spent around $3,126. There was also unnecessary or unexpected shipping costs towards the end of the project with ordering faster and expediting shipping. But that's where we're at.
Yeah, just to recap some of our final deliverables, we're happy to announce the sun sensor has met the 3 objectives. The sun sensor does return a numerical representation of the sun's position and sun's angles. The sensor also does have the ability to be fully upgraded into a space grade equivalent so that it can withstand the conditions of space. And the sensor can integrate with Astrobotic's existing hardware as the communication protocols are designed to be in line with that.
And on the testbed side, we do in fact have a physical light source. Additionally, we have a simulation that does track the sun tracking scenarios that can be implemented in. And we hope that the testbed shall interface with Astrobotic's simulator. We haven't had the chance to test that, but we're hoping it will function as anticipated.
Yeah, just looking forward for where this project would go once it's in Astrobotic's hands. The obvious transition for the sun sensor is moving to the new photodetector. This photodetector should be very easy to implement. One board, we already have it modeled with one footprint change. This will implement perfectly with everything that's already designed and increase our field of vision from 36 degrees to 75 degrees. The gain and the filtering board might need to be tweaked, so we developed a MATLAB script that once you take the photo responsivity of the new sensor, plug it into this script, it should give you the ideal amplification value. Your deal with this one.
As far as the test bed goes, the light source, as it is right now, the startup is a little slow and a little laggy. So something that could be fixed in the future is either replacing altogether or adjusting the dimming module so that we have a light that's going off to the races right at the start. And the next one would be the encoders to be properly integrated to the motors, so we allow for more accuracy.
We would like to sincerely thank all of you for coming and hearing us out today. If, Noah, are we good? We would like to try a live demonstration.
You good?
Yep.
Okay.
Get power on, and the light on. Okay.
You're good? Okay. Fine. There you go. All right, so as you can see, the testbed is running right now. The blue arrow there is where the testbed actually commanded location to, so what the simulated sun is looking at, and then the yellow vector is what the sensor is actually reading in real time. So as this is actually moving around, the sensor is sending live feedback directly to the controller and saying, here's where we think we are oriented, and we can see the exact error. As we mentioned before, the sensor is not currently calibrated, so we get a maximum of about a 3-degree error without being calibrated. To compare to commercial sun sensors, they typically get around 0.5 to 1 degree error, and that's post-calibration. So we feel confident that if we were to fully calibrate this sensor and do a lot more testing, we could get that number under that 0.5 degree requirement.
And then from there, we would be very happy to field any questions. Yeah?
So you guys mentioned that some of your requirements involve making sure that this can withstand the vibrations that it will encounter, the sensor will encounter in space. Make sure that they would withstand any shock or vibration loads.
Yeah, so that would be in the next iteration of the analysis. A solder joint analysis should be done to see if the soldering and each individual component could actually hold up to the vibration of the power. So it wasn't done in this iteration, but it should be done in the next.
So you all said that there was a checksum program, I believe you said in the one of the chips. If you have any other faults or any failure in the program itself, how exactly do you isolate that, and how does the operator detect that?
We have two sources of this. One in the program side. If we have any faults in terms of data integrity, there's a status register that gets, anytime a message is received, it can send out the current status of the sensor. And this will say if there's any current faults, data that doesn't look correct, things outside of the expected ranges, as well as making sure both communication lines are working. You want to add anything about the CAN system?
Yeah, CAN actually has a built-in checksum as well, and then it also is fail-safe biased, where if there is any state on the lines that is unknown or unconfigured, it actually turns the transmitters off so that it can keep the line secure, so any other things on that bus line that are trying to transmit data are not interfered with.
Also, if anything on the main processor were to fault out during operation, there's a watchdog protocol, which basically says if the sensor is stalled out and they're not receiving any new thing, it just completely reboots the system and starts it over. This would allow, if there's any weird errors that happen while in space travel, you could at least start the system over and then send out information that something was going wrong.
Test bed, why did you guys choose different gearboxes for housing elevation meters?
Yes, so I chose the 4-to-1 gearbox on the side motor just because it was a lot lighter than the one on the base. And we were trying to keep that as light as possible as we were going through the motion. We wanted to make sure that we weren't trying to oversize our gearboxes by any means. Plus, the 4-to-1 gearbox was actually about $16, whereas the one on the bottom was about $110. So it was very much a, cost-effective choice.
So are there any other areas beyond calibration that you guys would like to investigate to help improve the sensor's overall accuracy?
Yeah, a couple of those is right now the sensor housing, as you might have seen, is a stainless steel. It's very bright and shiny. Near the aperture, this can create reflections of light that can hit onto the actual photodiode surface and cause error. The typical way of dealing with this is you do a process called anodizing the inner ring of that aperture. This will reject a lot of that ambient light. So that's something that we weren't able to get fully anodized housing in time based on the lead time that it is to actually do that for an outside vendor. The other thing is, like I said, temperature calibration is not something that we've currently gone through and done. What you need to do is put one of these sensors into a full temperature system, which can scale it up over the course of a day or so, send that data out to a computer, and then read the values of those photodiodes at each temperature. There's already a system in place on the microcontroller where you could store that information, and then at any temperature you could just automatically subtract out dark current to correct those errors.
On the housing, was weight a big factor for your design when you design the housing, and like other kind of avenues to reduce weight?
Yeah, so the requirement for the actual weight was as low as possible. It wasn't actually number, mass and weight as low as possible. So that's why I chose 6061 aluminum. It's very light, very strong still. So that's kind of how I accounted for it. It's also 8 centimeters by 8 centimeters, so very, very small relative. So it's not very heavy at all. And the gearboxes also took care of any other weight issues on the actual test bed.
You know what the final mass gain is on the sensor?
I don't off the top of my head.
With materials of construction, did you consider anything else other than 6061? Or, a lot of it's due to cost. Did you consider anything else? Would you consider anything else?
I think we could consider anything, other things, but just in initial conversations with Astrobotic, they said 661 aluminum is perfectly good from their end. When we actually manufactured it, we actually had 7075 aluminum on stock. So we used that just because it's a little bit higher quality. But if we're going to actually manufacture a lot of these, 6061 is a lot cheaper and still holds up just fine. So it is a good choice for this.
With the stress analysis your team did on the housing, with random vibrations, was there any sort of fatigue life analysis done instead of just maximum yield stress analysis?
No, it wasn't. It was just, yield and deformation. The yield, the stress you saw was 1.17 megapascals, which is very low, so it wasn't a huge concern. So I didn't push that far quite yet, but that definitely could be done for the iterations.
For when fully upgraded to space-grade parts, do you know what radiation tolerance you achieved here?
Off the top of my head, it's the standard number that was given to us in that requirements document. I don't know what that number is off the top of my head. I'm not too familiar with accreditation results. We did check each component that had a RAD equivalent version that met that specification for any of the active components. As far as my understanding, the passive components wouldn't need to be upgraded, but everything else we found parts that were equivalent for. Very cool.
What was the one aspect of your project that seemed technically most challenging and that you were most relieved and pleased that you overcame that challenge?
Yeah, I'd say everybody had this.
Nice.
I mean, RS-485 could be a challenge with programming our own communication packages and how that works. And it proved to be quite the challenge to come up with how that would result. And then actually seeing that come about and then trying to troubleshoot your own issues is a little different than troubleshooting someone else's. Oh, and then on top of that, we had an issue with CAN bus where, was it 8 milliseconds?
Yeah, it was supposed to be 8 microseconds,
8
and it was
microseconds.
7.93.
Yes, 7.93 microseconds for timing between each bit, and CAN bus needed 8 microseconds, but only has a tolerance of 0.5. Our tolerance was 0.53, and so we had to manually go into the microcontroller and tune the clock. And that took many days to figure out what was wrong with that. Well, an afternoon.
Time for one more question.
What was the most expensive thing you destroyed during the course of this?
I think we're good on this. I think the only thing we took out was a Arduino R4.
Well,
Oh, yeah.
We just scratch that. As we mentioned, the photodiodes, we wanted the part that we wanted in from Hamalatu, and that part was delayed and it didn't look like they were going to get there in time. So we did have an idea that we could still achieve our 75 by 75 degree FOV requirements by physically cutting open a sensor. We did this the first time, and we did it in a machine. What's the machine called?
Wired EDM.
Yeah, wired EDM. So we didn't like just take some scissors or something in the actual building. We cut it open, and the first time it severed the wires that were connecting the actual photodiode to the pins. So he said, we're going to try one more time, and this time we won't sever those connections. And we didn't sever the connections this time, but for whatever reason, the process of cutting the thing open still rendered it inoperable. So that was two $120 photodiodes.
Not to give away the secret sauce, but that is something we have done. That is true ingenuity.
More desperation than there was ingenuity.
All right, well, thank you to the team.
All right.
A big thanks also to Astrobotic. It was a phenomenal time. We've got space exploration being led right here from Pittsburgh, Pennsylvania. I'm really glad that our students get to participate in that event in this way. There's now 10 minutes between now and the 6:50 start of the next presentations. So if you'd like to remain in this room, that's fine. But you do have time to change rooms if you want to